Okay, so before we get into the reading, I've got kind of a throwback problem for us to talk about together, although there's a lot more information than I normally would have given you in the past. But maybe in the past I would have given you a problem with like this much information. Find a function which satisfies this point and has this slope. Do you remember how we would do that? Yeah, point slope form. Or maybe how would we do that if we increased, I gave you an extra derivative.
You just throw it into kind of like a quadratic thing. So you do the point like, yeah, you do like x minus 0, x, and then you do like -1 plus 5x, and then plus 1/5 x squared.
That's a pretty reasonable guess, don't you guys think? Okay, and if we went all the way out, then we'd probably just have like a minus 12x cubed. If we went out to like the third derivative, probably. Maybe. We keep going with that logic. Okay, how about let's work backwards. So let's say if I've got a third derivative is -12, and I want to work all the way backwards to generate some function with this. Couldn't I, if I'm starting with a super deep derivative, couldn't we work backwards and undo some of these derivatives? Okay. All right, so, well, the antiderivative of the third derivative would just be the second one. Now, this is a constant, so I'd have to turn it linear. But, yeah, everyone's favorite. You know, I just got a text from a kid last night. He graduated a year and a half ago. And he said, I would have gotten 100% on my Calc 3 quiz last night. But he forgot plus C twice, so he got an 85.
85? Oh.
Plus C. Don't forget your plus C's. Anyway, hold up. It was just a quiz. It was just a quiz, so it's probably like, you know, 2 out of something weird. But anyway, just telling you. Just telling you. How could I solve for the plus C? Yeah, that's where this the points start to come in handy, right? So you'd say like, okay, f double prime is 0. That'd be 1/5. And then when I plug in 0 for x, okay, well I can solve for c. C then would have to be the 1/5. So I would know the second derivative of the function I'm trying to generate would be -12x plus 1/5. Mr. Hawks, I have a question. Okay. Yes, it was going to be why is your voice so loud? Okay, so let's keep going. We want to get all the way to the function f. So let's go around the block again. The antiderivative of the second derivative would have to get us back to the first one, right? And then, okay, let's see. Well, we have a linear thing, so it'd have to become quadratic. So power rule, I'm going to divide by 2. Now I've got my constant. I'm going to make that a linear thing. And then, again, don't forget your plus c. Okay, so let's repeat. I got another point. Let's solve for the c real quick. So this time we'd have 5 equals 0 plus 0 plus c. I chose 0 to make that work out nicely. And while we're here, I'll go ahead and divide -12 by 2, because that's not the worst thing in the world. And we should only have to run through the block one more time to generate whatever function we were intended to come up with. Let's see. I want to be in Mr. Hawks' class today, man. They're doing something fun. They're not anti-deriving over and over again. Okay, so not the worst thing in the world. was a lot of work, but individually, every single thing was pretty easy, right? It was just power ruling over and over again, plugging in points, that sort of thing.
Yeah.
You know those crappy old infomercials from like when you were little kids? There's got to be a better way. That was a lot of work to do that, wasn't it?
Anti-tabular?
Anti-tab. We'll come up with something. How about this? While we're here, I just want to show you something. So we're used to cleaning up things like -12 over 2, and then down here, what we had the 5 times 2. If we hadn't done any of that, I just want to show you what it would have looked like, because that might be helpful later on. Might be. Who knows?
That's cool. Oh man.
Factorial.
What do you mean?
Ding, 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 ding.
I thought that at first, but like I thought the numbers like 12, 1/5, and 5 didn't have like a correlation.
Backwards. People watching the video can't see this right now, but that was my evil grin. Yeah, this looks like a factorial. I mean, this would be 3 factorial, 2 factorial, 1 factorial, maybe 0 factorial? Remember, 0 factorial is 1 because some mathematician said so and it's convenient? Huh. Okay.
Is there like
And
a-
proved it.
Oh, okay. It's like, what's mathematical?
Google.com.
Okay, yeah.
Okay, so our job today and over the weekend is to figure out how we can make this process of generating a polynomial more systematic. So the first thing I want to just lay out is what a general polynomial looks like. So we'll say any polynomial, is that show? Yes, it is. Built or centered at the x value a. We're just going to say, so this is wherever we're building our model, because again, remember these polynomials are going to be models for something else. That polynomial would look like this. It'd be f of x or p of x for polynomial if you like. You'd have a constant plus some linear term, and that linear term would have its own constant. A multiple, something that helps you figure out the slope. You'd have a quadratic term, and it would have maybe a constant multiple, right? I'm just going to repeat this down the line a few more times. You could have a cubic term with a constant multiple. I'm going to stop at the 4th, but obviously this would extend forever. So what I want to show you today is how we can build something like this with just a few bits of information. The way we're going to get there is, well, the exact reverse process of what we did in what we just did on the front page. So if this is what our answer looks like, now granted we'd have numbers for all the C's, we'd have a single number for all the A's. Let's run down the line, let's derive this a bunch of times. Because, like, look at the last problem. I gave you a bunch of derivatives, right? Might be kind of meaningful. Let's run down the line and derive this a few times. So, like, the first derivative, well, our constant term, the derivative of any constant is 0. Okay, so that's gone. And then my linear term, what would the derivative of this guy be? Just the constant, okay. And then, okay, what about my quadratic term? There you go. So power rule, bring down that 2, reduce the power by 1. Same thing over here. Bring down the exponent, reduce the power by 1. Dude, if this paper wasn't stapled so weirdly. Okay. And again, let's just keep going. Okay, so the second derivative then, we lose our constant that originally came from the linear term, but we at least still have 2 of the second constant. Now over here on what was originally the cubic term, now we're going to have 2. And again, let's leave it as 2 times 3 just to see how it works out. But you're right, it would be 6. Now I'm going to do this all the way down through the 4th derivative. So fasten your seatbelt if you haven't already. How have you not? I mean, this ride has no brakes. You know that. Okay. Third derivative.
Megabyte?
What? What? Okay, we lose the constant.
Have some megabytes.
Making sure, goodness. Some people.
Do you not have megabytes in your phone?
I'll eat cold shit enough to know.
Okay, and then finally a notation thing. At some point, it gets really annoying to keep increasing the prime of the derivatives. The standard notation is you can go ahead and write however many derivatives once you get past 3. Officially, it's supposed to be in parentheses like this. That way it doesn't look like f to the 4th power. The parentheses I know. Honestly, if you write f4 in the context of this, I'm going to know what you mean. But for the record, officially, that's what it's supposed to be. And we'd lose that constant. We'd finally just have the 2 times 3 times 4 times the 4th constant. Okay, so, well, I'll give you a second to catch up. I took a little more room than I anticipated. Oh, well. Okay, so what are these magic constants then? Well, if we look at where we are centering the polynomial, we'd always be evaluating at x equals a to figure out each of these constants. So like the function's actual value at a would zero out all of these other terms, right? Because you'd have a minus a, 0. A minus a squared, still 0 squared. 0 cubed, 0 to the 4th. So if you plug in the center, we should get out just that constant. And oh yeah, if I plug in the center, or I plug in the center into the first derivative, well, if I plug a into the first derivative, I'd get c1 plus 0 plus 0 plus 0, okay. If I plug the center value into the second one, well, I'm going to get double the second constant plus 0 plus 0. You see where I'm going with this? If I plug the center into the third derivative, I'm going to get maybe 3 factorial. Is that fair? We've seen that pattern a few times now. 3 factorial times the third constant. Man, I ran out of room here. Same thing with the 4th one. So again, my purpose of making you work it through this way was to see how could we take this and how could we reverse it. Basically, is there a way where we could build a polynomial if I just gave you a bunch of information about the derivatives? Looks like it. If I told you, hey, the third derivative at this point is something, you could be like, okay, well, if I know the something and I know the point, I can figure out the constant that would help me build the cubic term of the polynomial. So we're kind of going to work backwards. If we were to rearrange these real quick, first off, see how we had like factorials on some of them but not all of them? You really have them on all of them. We could stick a 1 factorial in on the constant. We could put a 0 factorial in here on the first one. I'll make a little list over here that's cleaner. How about that? So for example, the actual function evaluated at the center should give us 0 factorial times the 0th constant in our polynomial. And let's just go down the line like that. So first derivative evaluated at the center would be 1 factorial times the first constant. Second derivative, 2 factorial, second constant. Okay, so these numbers are they're different than the ones I gave you on the front, but it's the exact same style problem. Find a function that matches this given information. We could always be like, well, I know f of 2 is 24, so I'll anti-derive both sides. I'll solve for c. Do that a bunch of times. Or let's just see if we can kind of reverse engineer this. If we know we want to make a polynomial that looks like this, then really all we need is all the c's, all the c0, 1, 2, 3, 4, and we need to know what number we're going to plug in every time for a. Well, one of those is pretty straightforward. What number are we going to plug in for a? 2. That's where all the information is at. Okay, so the center of our polynomial is going to be 2. So f of 2 is 4. So 4 equals 0 factorial times the first constant. Again, 0 factorial is 1. So I know the first constant, or the 0th constant, in my polynomial is just going to be 4. And same thing with the 1 factorial. So the first derivative was negative 3. So negative 3 equals 1 factorial c1. C1, also negative 3. So the first two are pretty much gimmies. You have to start dividing once you get into the bigger factorials, obviously. So let's see our second derivative. Am I going too fast? Okay. So our second derivative, let's see, is 8. That was 2 factorial times the second one. So then our second constant is 8 over 2 factorial, which is also 4. Let's see, our third derivative is negative 10. C3. Okay, so the third constant would have to be negative 10 over 3 factorial, which would be negative 10 over 3 times 2, which would be 6, which you could further reduce that, I guess, if you wanted. Now let's see, what was our last one? 24. Which, let's see, 4 factorial, well, that'd be 6 times 4, which, oh, hey, that's also 24. So, our polynomial in standard form, well, I guess substandard form, but almost standard form would be, how about, okay, I don't want to use the phrase standard form because that's what your Algebra 2 teacher said for something else. Our polynomial that looks like this would be, make sure this is high enough for you. Hello, thank you. Let's see, Abby, this is for you. It has question marks.
Nice. There's like 3 separate questions.
Okay, so again, just following our pattern, our polynomial would be our 0th constant, which we said was 4, plus our first constant times a linear quantity. So our first constant was actually negative 3, so I'm going to say minus 3 times, and then a linear thing that shows the center. So it was x minus a up here. I'm going to use x minus 2 because that was our a. Let's see, plus our second constant, which is 4, times our quadratic term now. Let's see, our third constant was negative 5/3. Our fourth constant was 1. I'm going to leave the 1 just to show it's there. So it was a lot of writing. Would you do this much writing if you had to generate this polynomial again? Probably not. I was like very explicit in how I laid everything out. But isn't it kind of cool how we can build a polynomial if all we have is a bunch of derivatives at the same point? That's huge. Up until this point, I would have told you if you're going to build any order, let's say nth order polynomial, you would need n plus 1 pieces of information. What that means is if you want to make a linear function, that'd be degree 1, then you need n plus 1, so 2 pieces of information. You need 2 points, or you need 1 point and 1 slope. If you want to make a quadratic, that'd be a second order polynomial, you would either need 3 points, or maybe 1 random point and the vertex. You might be saying, Mr. Doolin, that's 2 points of information, or two bits of information, a point and a vertex. Nope. The third bit is knowing that that second point is the vertex. I know. So, it's not that you need n plus 1 points to build an nth degree polynomial. It's you just need n plus 1 pieces of information. I think that's so cool. And this is how we can build a polynomial that models any function. I did this with random numbers. But think, if I know the fourth derivative of something that's hard to, what's a hard function to evaluate? Sine. If I know the fourth derivative of sine somewhere, and all the other ones, the third, the second, the first, I can build a polynomial for sine. And now I can evaluate that polynomial at the random values that aren't on the unit circle. Dude! That's so cool!
Yeah!
So that's the purpose here. Again, I gave you random numbers this time, but we can generate derivatives on any function. Final note, it is okay that this is unsimplified and not in standard form. So you also could have left this as like 4 minus 3 x minus 2 plus, what was that originally, 8 over 2 factorial, minus 10 over 3 factorial. It is gross, but here's the thing. Not everything simplifies so cleanly. And if you needed to identify a pattern, like a sequence, it's going to be a lot easier to identify said pattern if you don't simplify things. Because, hey, look, my denominator's pattern is 0 factorial, 1 factorial, 2, 3, 4 factorial. Okay, the numerator has no discernible pattern, but that's because I picked random numbers out of a hat. My point is, if you needed to maybe generalize this and tell Mr. Doolin how to make any old term, maybe the 20th term if you wanted to, you could. So you might not always be simplifying these guys. So the work we did right here is basically 2/3 of the work to generate any Taylor polynomial. The only shortcut I took is I gave you all the derivatives. If you need to build a polynomial from scratch, you'll have to take the derivatives yourself and evaluate them so that you can do what we just did here. At this point, I think we're ready to start reading. If you flip over to the next page, you'll see the things that I want you to look for. We did kind of stuff that basically mimics the first 4 examples and the first 2 practice problems, so don't even worry about those. probably would be worth your time to try the others as you read along. And then I've just left you some headings here for things I definitely want you to look for, things I definitely want you to summarize. This is basically the definition of how to build a Taylor polynomial. Well, nope, that's false. I'm going to take that back. This is the rules, like this has to be true about your Taylor polynomial. This one's the definition. Duh. Ooh, I made a mistake here. Difference between degree and order. Although power means degree, but he just uses the word degree in the book, so I'll stick that in there. And then when you get to page 41, we'll talk about that. There's a bunch of equations. We got to memorize some of them. We'll come back there. So I'm going to stop the video for the people who are gone. It's time to read.